Welcome to my lecture on confidence intervals. We're going to begin by talking about the t-distribution because that's going to be really important for us in this to calculate confidence intervals. Okay, so what I have displayed on this graph is the t-distribution. The dashed blue line represents the normal distribution. It's the standard normal, and standard refers to the fact that the mean is 0 because the peak occurs right here at 0, and the standard deviation is 1. Now, in this green curve, the degrees of freedom of the t-distribution, so the green curve is a t-distribution, and a t-distribution has what's called degrees of freedom. And the degrees of freedom begin at 1, and they keep going to be as large as you want, okay? But they have to be an integer. So this is 1 degree of freedom with this green curve. And as the degrees of freedom increase, you can see we get this red curve, and that better approximates a normal distribution. And it's a fact that the degrees of freedom, as they increase and become very large, the t-distribution becomes a normal distribution, okay? And the degrees of freedom for a t-distribution for us is going to be the number of observations minus 1, or at least in this chapter. That can change in other chapters, but for this chapter it's just 1 minus your sample size. So when does a t-distribution arise? This is when it arises. Okay, so I apologize that. Okay. So this is the t-distribution, and it's the same as the z-score, except instead of using the population standard deviation, you're using the sample standard deviation. So the t-distribution with n minus 1 degrees of freedom arises when you use x bar minus the mean divided by the sample standard deviation over root n. Okay. And let's just define what each of these terms are for clarity. Okay. So that S, that's the sample standard deviation, and that's calculated from your sample. N is your sample size or number of observations. X bar is the sample mean, and this mean mu, that's your population mean. It's either known or unknown, but in this scenario it's unknown for this section. Now, to calculate probabilities with the t-distribution, you can use your table, and there's one in the back of the book. It's table VII for your t-distribution, and it should look something like this. And this is a little bit hard to make out. Or you can use an online calculator, and I'll show you an online calculator that I use. Okay. So one thing that I like to do and use is I like to use a percentile, and I want to find a value which captures 97.5% of the data. Okay, and this is equivalent to having between negative 2.03 and positive 2.03, having 95% of the data. Okay, so let's look at an online calculator. Okay, so I'm going to go to the online calculator, and if we go to the online stats book, as you see it right here, and I click on calculators, the contents, I have the inverse t-distribution, and I also have the t-distribution. Okay, the inverse t-distribution is used for confidence intervals, so I'm going to use that. Okay, and I want a 95% confidence intervals, so technically I can have any confidence I want. I could have a 98% confidence interval, but this table is only built in to find a confidence interval for 99%, 95%, or 90%. Okay, so I said 35 degrees of freedom, I want a confidence level of 95%, and I get 2.03. So that is how I get this 2.03, and that's why I have this 95%. This 95% is the probability it's between the two values. Okay? And okay. So here's my example. I have a random sample of 36 unemployed individuals, and I have calculated their sample mean age, and that's 32 years. The sample standard deviation is 9 years, and I want to calculate a 95% confidence intervals. So I'm going to play this game that I encourage you to do when you're doing confidence intervals, and it's called Name the Variables. Now, before I do that, I want to emphasize that a confidence interval is very practical because it estimates what you would think the population mean age of unemployment is. Okay, but it's very hard to obtain the true population mean, and so a confidence interval is much more practical. And the reason why it's more practical is because if I want to obtain the true population, I'd have to somehow be able to identify every single unemployed individual in the population, and then calculate their average age. It's very time consuming, if not impossible, to be able to identify every single individual who is unemployed in the population. Okay, so instead I can take a random sample, or as best I can a random sample, and calculate a confidence interval. Okay, so let's go on with calculating the confidence interval. And the first thing I'm going to do is I'm just going to identify the given information. I have the sample average is 32, the sample standard deviation is 9, the sample size is 36. I have a 95% confidence interval, so alpha over 2 is 2.5%. And I'm going to talk a little bit more about what this 2.5% represents. That's alpha over 2. Okay, but let's proceed with the confidence interval. Confidence interval, what we've calculated is the probability a t-distribution with 35 degrees of freedom is between minus 2.03 and positive 2.03 is 95%. But a t-distribution is equivalent to this. Okay, and it turns out I know the sample average, I know the sample standard deviation, and I know the sample size. So the sample average is 32, the sample standard deviation is 9, I have 36 observations. The only thing that's not captured here is the population mean. So we're going to just solve this equation for the population mean mu. And when I do that, I get this equation. So I just have to move the 32 to the other side and remove the negative. Okay. When I do that, I get this. Okay, and it says 95% of the time the mean is between this number and this number. Okay, that the mean is in the interval 95% of the time. Okay, and I can break that down. The only difference between the greater than part and the less than part is the negative. So this confidence interval is calculated by 32, which is the mean, plus or minus that 2.03, which shows up, times 9 over root 36, which is 3/2. Okay, so I calculate what these numbers are, and I'm given that the population mean is contained in an interval from 29 years of age to 35 years of age. Okay, I want to say the random part is the interval, not the population mean, because the population mean is a single number. So it's an important distinction that the 95% refers to the probability that the interval contains the mean. Okay. So let's look at this form of the confidence interval a little bit more. Like I said, this part 32 that represents x bar, this 2.03 that represents a t-distribution, and this 3 over 2 that represents the sample standard deviation of 9 divided by root 36 or root n. Okay, so if I had to come up with the form of a confidence interval, it's going to be this: x bar plus or minus that number which comes from the t-distribution, okay, times its sample standard deviation over root n. So if there's one thing that I want you to get from this lecture, it's that if you need to calculate a confidence interval, use this formula, okay? And the level of confidence is 1 minus alpha. So this alpha over 2 relates to the t-distribution, the number that you calculate, okay? Let's work another example. Let's find a 99% confidence interval for the mean time required for an oil change at a local company. Okay. So for quality control reasons, like you want to know how fast you can change an oil, how many cars you can fit in a given day. And so we're going to take a random sample of n equal to 30 oil changes, and we're going to compute the sample average mean is 17.2. And the sample standard deviation is 6 minutes. So here we're just going to name what we know. Here's the sample average. Here's the sample standard deviation. Here's n. So I calculate degrees of freedom as 29. The confidence interval is 99%. So alpha is 1% and alpha over 2 is 0.5%. Okay. Now I get this number 2.756. You can either get that from a table from the t-distribution, or we can use that same calculator. I want a 99% confidence interval with 29 degrees of freedom, and we'll calculate 2.756. Okay, and that's exactly the number we got. Okay. So now if I want to calculate a confidence interval, I just need to remember the form of a confidence interval. That's the formula from this last slide. So I just use this and I write that down. I know what x bar is. That's 17.2 minutes plus or minus this 2.756 that comes from the t-distribution divided by the sample standard deviation, that's 6, divided by root 30. So it says you would expect that the mean would be contained between 14.2 minutes and 20.2 minutes for an oil change, okay? And so this gives you an idea of the population average time required to change an oil, okay? Now, one thing that I want to point out is that the confidence interval is 99%, and alpha is 1%, so alpha over 2 is 0.5%. Let's talk a little bit more about that, okay? So 1 minus alpha, that's 99%. This contains the mean. That's the probability the interval contains the mean, is this 99%, which is right here, or 1 minus alpha. Then you have alpha outside of this interval. So half of alpha goes in this left tail, and half of alpha goes in this right tail. And that's what this 1 minus alpha represents. And this is the t-distribution. That's what this blue curve represents. Okay. So just a little bit more detail on that. Let's do another example here. Okay. It says the mean birth weight of preterm newborn babies at a local hospital is 4.8 pounds with a sample standard deviation of 3 pounds in a sample of 36. Let's construct a 95% confidence interval for the mean birth weight. Okay, so we have the variables that we know. We know x bar is 4.8, s is 3 pounds, n is 36, so degrees of freedom is 35. We want a 95% confidence interval. So alpha is going to be 5% and alpha over 2 is 2.5. We used that online calculator. We got that number 2.03 before, so we're just going to reuse that. Okay. So we write down the form of our confidence interval. That's going to be our average, plus or minus 2.03, plus the sample standard deviation over root 36. This gives us 3.785 pounds to 5.815 pounds. And I want to emphasize that this does not mean that the population weight of preterm babies is between that. This confidence interval represents the probability that the interval contains the mean. Okay. Okay. Let's look at an actual study that was done. and this was the sex discrimination in employment, and it's data on employees from one job at a bank. The data has 32 male and 61 female employees, and our goal is to construct a 95% confidence interval for male starting salaries. And I used software called RStudio to compute the analysis, and I'm just going to output it for you. This is the command that I would use, and I've left some commands out because I'm not asking you to use it, but I am asking you to interpret the output. This is the one sample t-test, and what it outputs the 95% confidence interval. I could change that value to be a different confidence level if I wanted, but this is what the confidence interval is. It's 57.07 to 62.05, and it returns to me the average value, the sample mean of the males is 59.56. Okay, so the confidence interval is that their starting salary is from 57.07 to 62.05, and that's what you would expect the average starting salary to be in, and the 95% reflects the probability that this interval contains the mean. Okay. Now, as you can see, the confidence interval has this form. Our estimate for the population mean is the sample average, okay? But there's a margin of error. So you add or subtract a certain amount of error. And this part right here, that is called the margin of error, okay? So the general form of a confidence interval takes the form of a point estimate, which in this case is x bar. There'll be different point estimates, and a margin of error. So that's the plus or minus part, okay? We're going to call this part right here, that's our margin of error. And if I want my margin of error to be a specific size, I can do that. And I'm going to call that margin of error E. It turns out the margin of error gets smaller and smaller as you collect more data, which is a good thing. You would want a more accurate answer as you have more information. Okay, so if you want to specify the margin of error, and you want to know how large of a sample you need to estimate that margin of error, or to get that margin of error, this is it right here. This is the formula that says if you want to estimate the population mean to a certain margin of error, this is the sample size that you need, okay? So let's go ahead and do that. Let's calculate a margin of error. Okay, so remember we had a random sample of 36 unemployed individuals, and it's found that the sample mean is 32 years of age and a sample standard deviation of 9. So here's my question. It's not to compute the 95% confidence interval, we've already done that. But my question is, what sample size would be required to have a margin of error of 2 years based on this data? Okay. So one thing that you should notice in this formula is it doesn't have a t of alpha over 2, it has a z of alpha over 2. So let me show you where that comes from. This z of alpha over 2, well, alpha is going to be 5%. 1 minus alpha is going to be 95%, so alpha is 5%, and alpha over 2 is 0.25. That's 1.96. Okay. And so this is one piece of information we need. We need to get that 1.96. So let's go to this. I'm going to go to the calculator section on that online stats book. And I'm going to go to the inverse normal distribution. And it says this is used for confidence intervals. Okay. And I want 0.025. I want to have a mean of 0, a standard deviation of 1, and I'll have it be above 1.96, because remember, the alpha over 2 goes in this tail, okay? Okay, so above, so if I want area of 0.25, That's the probability. Mean is 0. Standard deviation is 1. I press recalculate. It gives me this 1.96. That's exactly what we have listed here. That's the 1.96. So this 0.025, that goes in the area when we do this calculation. So here's the area. The mean is 0. The standard deviation is 1. You should always have mean 0, standard deviation 1 when you do this z. Okay. So I plug in this 1.96. I have an estimate of the sample standard deviation S. That's 9. I want the margin of error to be 2 years. So that I specified the margin of error here. Okay. And so I plug in 2, then I square this quantity once I compute it, and it looks like I need 77.79 or 80 observations to have that margin of error. Okay. And I would really emphasize that it is very costly in a study to obtain observations. Okay. I'm not going to go into more detail, but I'm just going to say it is costly. So if you want to have a specific margin of error, and it's a lot more observations, it's going to cost you time and energy and money. Okay. Okay, so when you're doing confidence intervals, there are some assumptions. And here are your assumptions. The main assumption is either the data is normally distributed or you have a sample size of 30 or more. Okay, the data should be independent and identically distributed. Independent and identically distributed, that will be satisfied if you have a random sample of your data and they are all from the same population. So independent, it means you have a random sample. Identically distributed means that they all come from the same population. Okay. If your data is less than 30, you should check the normality of the data using a histogram or box plot. Slight variation shouldn't matter that much as long as your samples, the closer your sample size is to 30, but the further away it is from 30, the more having a skew matters. So if your sample size is less than 15, you should check that the data ideally has no outliers and that it's symmetric, and you should use a box plot to assess that. If the sample size is between 15 and 30, you should just check that the data isn't skewed too bad. Okay. So the next topic I'm going to talk about is confidence interval for proportions. That's all that we have for confidence intervals on the population mean. Thank you for joining me.